And ultimately remembering that as I look at my equations, those letters don't change and they don't mean anything different no matter how my information is given to me. So no matter the fact that my information is now given to me in words or in a table of data or whatever it is, the fact that it's given to me in a table of data doesn't change what an amplitude is, the distance from my midline up to the maximum value. It doesn't change what phase shift means, which would be where we start our graph. Those things, those ideas don't change as our information given to us does. Okay, so keep that in mind. All right, so what is this idea of harmonic motion, modeling harmonic motion? In the real world, there are a lot of things that have what's called periodic behavior, and what we are looking at is graphs that have periodic graphs, meaning they do the same thing over and over and over again. And things in our world that do that, the rise and fall of the sun, right? We could track that, and it would, if we were to mark down the times, it would be a very periodic, repetitive thing over and over, right? Something that doesn't mean much to us in Nebraska, but if we lived on the coast, tracking the high tide and low tide. Tracking things like the monthly temperature. If you think about our temperature in Nebraska, right now, January, February, we're down here at like an average of, 30. We get to July, it's going to spike up here to our 80s and 90s, and then as we head back to December, it's going to decline again, and guess what? It does that same exact motion next year and the year after, and so if we were to track it year after year, a great picture for that would be using a sine or a cosine. Those that are in physics, you see these things happening a lot with like oscillation, vibration, a mass suspended on a spring. We suspend a lot of masses on springs for some reason and track the height of that as the spring moves. All of that is what's called harmonic motion, if it's got a repetitive motion to it. And using a sine or a cosine equation, later on you're going to hear them referred to, sine and cosine, and grouped under this heading that's called sinusoidal. Okay, sinusoidal is a big fancy math word for sine or cosine. Okay, and it doesn't necessarily mean sine, even though the beginning of the word starts with like sinusoidal. It just means sine or cosine. Okay. So what is new to us today is this vocab word of frequency. Get out your notes packet. Frequency, again, understanding what it is great. Understanding how to find it is even better. But period was how long it took me to complete one curve, right? If I were looking at this as a sine curve, that would have been the period. What frequency does is it doesn't look at one curve, but it looks at one unit of time. And whatever this unit of time is that stops here, frequency counts, okay, then how many full curves do I complete in that set unit of time? Okay. The most important part you understand is that it is the reciprocal of the period. So frequency and period are 100% related by turning the other one upside down. There is no formula to it, no pi added or taken out, no 2 pi, nothing. You just have one, you turn it upside down, you get the other. Okay? So the difference in those side by side is this. The period tells us how long to complete one curve. Frequency says, given a period of time, whatever that period of time is, how many curves are finished in that. So if it's a day, how many of the curve would be finished in that day, or a year, or whatever it is. The formula for period, which we are very familiar with, is 2 pi over b. Well, if they are reciprocals of each other, that means the formula for frequency is b divided by 2 pi. I don't think it's worth memorizing new formulas. So I will run everything through this side because this is the side we know, and just remember that the reciprocal of period is frequency. With that being said, b is 2 pi over the period. Look, they don't look exactly the same, but if I were to solve this equation for b, which is right here, I would just multiply by 2 pi, right? So we can see that b would be 2 pi times the frequency. That's actually an easy one, and if that's something you can memorize, great, but not worth it because I can run everything over here and get to the period and just turn it upside down to find the frequency. Or if given the frequency, I can turn it upside down and get the period, figure out b. Okay, so we don't need to memorize these new formulas. Just understand the reciprocal part. Today we're going to be working with a lot of word problems. So one of the things that has to happen in a word problem is relaying whether we are writing our equation as a sine or a cosine curve. Sometimes they'll just come straight out and say, write it as a sine curve, okay? But sometimes they're going to tell us what's happening at the start, at the initial, at the time equals 0. And the other way of looking at that, if I visually could see on a graph time equals 0, that would be at the y-axis. So they're saying at the y-axis, at time equals 0, our graph's at a maximum or a minimum. They're using the words to tell us to write it as a cosine curve. If we were to visualize what's happening, here's time equals 0. If I were to graph something, and they're telling us it's at a maximum, I can see now visually that that would be a cosine curve. Compared to, they say, that at time equals 0, or at the initial, which again is our y-axis, that it's at 0, that would be a picture like this. I can see that that would be indicating that I'm supposed to be writing it as a sine curve. Now, again, if they're telling us to start our equation at time equals 0, there's one other thing it tells me about, and that would be my phase shift. If I'm starting my graph at time equals 0, what is our phase shift? 0, right? We're not moving right or left. We're starting at the y-axis. So other than telling me that it's a sine or a cosine curve, it's also telling me that my phase shift for both of these would be 0. So we kind of get that twofold information there. Which one to pick, sine or cosine? Phase shift is 0. Okay. So where is this going to show up in a word problem? They're gonna like throw it in as like a little sidebar, a tiny little phrase somewhere in there. So you got to kind of keep an eye out for that phrase. And this is what it could look like. And I highlighted it nicely for us on this one. But it'll seem like an afterthought. But it'll say something like this. Find a function that models the simple harmonic motion having the given properties. And then it says this. Assume that the displacement is 0 at time equals 0 becomes important to us. It tells us two things. If it's 0 at time equals 0, is that sine or cosine? Sine curve. And our phase shift is also 0, okay, because we're starting at the y-axis. After that, we have to then read the given information and think through A, B, and D. I didn't put C up there because we already talked about it there that C is going to be 0 if I'm starting at the y-axis, okay? Sometimes they're going to straight out tell you the information. Like it says amplitude is 15. If amplitude is 15, A is 15, right? No thought process on that. Sometimes they're not going to come straight out and tell you, because usually if we're looking for B, they're going to tell us the period, right? And we're used to that conversion. Given the period is 4 seconds, ooh, careful on this. If the period is 4, what is B? Pi over 2. It's always 2 pi divided by. Nope, they told us the period. Yep, they told us the period, and it's always 2 pi divided by the one they give us to get the other guy, right? So 2 pi divided by 4 would end up being pi over 2. And then this one, and this is, again, because we always need to think through all of our letters, but based on the information given, vertical shift, right? Nothing to indicate that there would be one or wouldn't be one, so then we just default to nothing, okay? So no vertical shift, nothing in there indicated that there would be one, so no, we wouldn't put anything there. So then putting this into our equation, y equals a sine, we talked about why it's a sine equation, right? 0 at time equals 0, so it'd be 15 sine, and then this is what's going to start bothering people today. When we get into real world data, it's just not pretty numbers. We're used to a nice pretty number there, but our b value is pi over 2. Understand that pi over 2 that's not a variable, right? So it needs to be b times x, so pi over 2x. No c value, no d value. Nope, they won't put an r. I mean, it would be comma rox or comma reflection over the x-axis. Yeah, if there were to be one. Okay, so then putting in that new word we just learned today, there's going to be more than one way we can attack this one, but given an amplitude of 4.5 and a frequency of 0.4 hertz. Okay, so again, the information at the top did not change. So we're still going to write this as a sine curve. We're still going to have a phase shift of 0. We want to think through A, B, and D. And I'm going to check off A and D quickly because they directly tell us the amplitude. Nothing, again, to indicate that there would be a vertical shift in this situation. So it's the whole frequency to B value thing that we need to talk about. First of all, at the beginning we said, okay, frequency and period are reciprocals of each other. And if I want to do a reciprocal, I want it to look like a fraction. They kind of try to trick us in this one, and it doesn't look like a fraction. But what is 0.4 as a fraction? 4 over 10, which would be 2/5, right? Okay, well, if the frequency is 2/5, that means that the period is what? 5 over 2. Nothing to do, like no changing, no adding or pi or nothing. It's just turn the fraction upside down, right? The only reason I say, that was not a question over here, was it? But we are way more comfortable finding B from the period than we are from the frequency, so I would just run it through what we know. So I know then to convert this to B, it's 2 pi divided by the period, which is 2 pi times the reciprocal, right? Multiply straight across the top, straight across the bottom, and I get a B value of 4 pi over 5. Now, could I have remembered from the other page, if I scroll back here 2 pages, that B is just 2 pi times the frequency? Yes, and we got the exact same thing that we would have. We didn't need to remember that formula, but if you did, it just kind of saved you a step, which is fine. Put all that into my equation. Y equals 4.5. Again, a sine curve because it's at 0 at time equals 0. Ugly B value of 4 pi over 5. Don't forget the x. X gets left off of these equations a lot because we feel like pi should be a variable, and it's not a variable. Okay, so those are kind of your basic ones, our intro into this. I'm going to give you one more that you guys can do on your own, but any questions up to this point? Okay, try this one on your own. A bass tuba can hit a note with a frequency of 50 cycles per second, which is 50 hertz, and an amplitude of 0.75. Sometimes they directly come out and tell you, write a cosine function. So you're going to write this as a cosine function, okay? That can be used to model the initial behavior of the sound wave associated with the note. All right, so the information given. Frequency is 50, amplitude is 0.75. Again, very quickly, if frequency is 50, what's period? 1 over 50, right? Just turn it upside down. There is no changing the number, no nothing. If we have one, we turn it upside down to get the other. It doesn't matter which one you have. You turn it upside down to get the other. And again, I would do that because I think we're comfortable with moving from period to B. 2 pi divided by the period, which would be 2 pi times, 2 pi times 50 over 1. Multiply straight across the top, straight across the bottom, and we get that B equals 100 pi. You could also remember that to move from frequency to B, it's just frequency times 2 pi is true also. Gets us to that 100 pi. So putting those together, I didn't talk about, we have A and B. C, it says at the initial behavior, so that's going to be no phase shift at time equals 0. Again, nothing to indicate that there's a vertical shift, so we wouldn't include that. Amplitude of 0.75, they directly told us cosine curve right here, so I picked cosine. B value of 100 pi, that's a number, so we have to have a variable in there also, 100 pi x. Questions on any of this? Kind of going the other way, given an equation, pulling out the information here. The equation that I'm going to give you on this first one, the displacement of a mass suspended by a spring is modeled by the function y equals 10 sine of 4 pi t plus 24, where y is measured in inches from the ground and t is in seconds. From that equation, identify the amplitude, the period, and the frequency of the motion of mass. I would start with just the amplitude and the period. Remember how to go from an equation to period. Just because our numbers got a little uglier, nothing has changed about our equations. Remember, it still goes A sine B times X. We don't have a plus C because there's no parentheses in there, plus D. Okay, go ahead and glance at your table partners, and you guys can look together because I'm going to ask you guys for answers here. Okay, let's go ahead and talk. Peyton, what did your table get for amplitude? I think a lot of us are really good at picking out the amplitude. It's the period that will probably have caught a lot of us. And Lily, I'm going to take the period from you. What did you get for that? 1/2. Okay, now I think there might be some discussion on that. A lot of times, again, we take the number we see in the equation, especially because it's got a pi, and we got so used to the period having a pi in it. But remember that this is B, right? And to move from B to period, you have to take 2 pi divided by, and 2 pi over 4 pi, your pi's cancel. And the 2 over 4 is where the 1/2 comes from. So she did a really nice job on that one. A lot of, again, I know we want there to, today it's not going to happen. Period is usually not going to have a pi in it on real world situation type stuff. It gets uglier, okay? So then moving from period to frequency, what is it? 2. Turn it upside down. Don't do any more work than that, okay? So taking all of that and translating it in then to a sketch of the graph. Very similar to what we were doing, except for, and again, it's going to bother some of us, but as we draw this, I'm still going to have 1, 2, 3, 4 tick marks along the x-axis or along the variable, which in this case is t in seconds. And we still label the 4th tick mark as the period. So what is the number I'm putting on my 4th tick mark? 1/2, right? Very different than what we've numbered it before, because so often it ended up being like a pi or a 2 pi or whatever. Well, the period is 1/2, and the 4th tick mark is the period, okay? Which would make this 1/2 of a 1/2 or a 4th. Now, we identified a lot, but there was a little bit more in that equation up there that we have to take into account as we go to draw our picture. What's the other thing that was in there that we need to take into account? Plus 24, right? What is that moving? Up 24, including our midline. Now, guys, you don't have to put 24 tick marks up here. What I want to see is that you know those kind of major benchmarks on our graph. So I know that we have a midline up here at 24. I'm just going to do that. Okay? You could. There are 2 other numbers that I would absolutely want to see on there if I drew that, though. Does anyone know what they are? 34 and 14. Where are those numbers coming from? The amplitude. If I move 10 above this, I would be up at 34. If I move 10 below this, I'd be down at 14. And I almost think that's a better way of showing that I know exactly what values I'm hitting than estimating, putting them between, like, if I numbered by fives or whatever, okay? So then I'm drawing a sine curve, does not have a phase shift, right? Because there was nothing added inside, which means my sine curve is starting on the midline at time equals 0. And then we just draw a sine curve like normal. So go over 1 up our amplitude, which is 10, back to my midline, over 1 down 10, which goes down to 14, and back to my midline. And that would be a picture of that curve. Correct. Yes. So we've actually kind of already discussed the next question based off of our picture, but sometimes the word displacement messes with people. Find the maximum displacement of the spring above the ground. All that is asking you for is what is the maximum value we hit? What is the maximum value we hit? 34. Your maximum, and again, those kind of big words are distracting, but it's asking you for your maximum. That's always going to be our midline plus our amplitude. Right? In this case, that was 34. If they had asked us for our minimum, it would be the other way around, right? Our midline minus our amplitude. Okay. Jonathan? What's that? Frequency, again, is just how many times that a complete curve would be done in like a set amount of time. So that one is used a little bit more on physics. Like we've got in 5 seconds, how many times does the weight oscillate back and forth type of thing. So just kind of an introduction to it. We, in pre-calc, don't use it often. Nope. Yep. All right. The last section that you see today, and it looks like we're doing a lot of these problems. Guys, we're doing one problem. I've broken it down into the 4 different letters, A, B, C, and D. You are still writing the equation of a line. So it is still going to be the same format, which is why we have to think through A, B, C, and D. Here's what I'm going to tell you. You will be much happier with yourself is as we take our notes, I don't just write the number here, but I explain to myself how I found A, because it does look very different as we do it from a table of data than it has from anything else we have seen. So a couple things as we work our way into this. One of the very common things that you will get in a table of data is something measured by months. So that they took like the high and low tide by month, or they took the temperature by month. We do a lot of temperatures by month. But it's not months. I want you to think of what they are as numbers. Like January is the first month, second month, third month. So you actually think about the number of the month, if we were to write that, instead of the name of the month. Okay. That in a table of data, the top row or the first column is always your x values, and that's what we would use to label our x-axis. That the second row or the second column is always our y values, or what we would use to label that vertical axis. Okay. And so I will be identifying on each one of these A, B, C, and D. Are you looking at your x's or are you looking at your y's? But you can kind of think through, like, what does that mean, right? And the last thing is that you're looking at this, we will be focusing a lot on only 2 values in there, really. And that is going to be where your maximum happens and where your minimum happens. So our maximum happens, as we scan through here, in July, right? So that's going to be one you're going to highlight. Always find your maximum. Scan through and find your minimum value, 32 in January. The rest of it is forming that curve. These are just ordered pairs. I could graph a picture of this. Like our first month is 1 up at 32. Second month, we're up at 38. Third month, 47, 59, 70, 80, 84, 83, 76, 64, 49, 37. It's starting that harmonic motion, right? And so there is a picture that goes with this. We won't draw it very often, like once or twice ever. But they are just ordered pairs, right? So your amplitude is talking about if I were to draw in this imaginary midline, how far above or below that our max and mins are going. And so it is up to down, which would be using our y values. Oops, so we would focus on those second numbers in there. And it really is going to be the distance between your max and min, and to find distance between numbers you subtract. So it is your maximum value minus your minimum value gives you the total distance, and then you have to cut that in half. So we'll always divide that by 2. There's your formula. Max minus min. How far apart are our max and min? And then divide that by 2 to find your amplitude. So in our example, our maximum value is 84. Our minimum value is 32. Okay, so 84 minus 32 would be what? 52. Divided by 2, 26. Okay, so we're just going to work our way through all 4 letters. There's A. Max minus min divided by 2. Questions on that? Okay. Second letter that we have in our equation is our B value. The B value, before we get into actually finding it from our table of data, if I were to have you look at just a cosine curve, okay? So if we were to start our cosine curve here at like a maximum, and then we hit our midline, and then we hit a minimum, right? And then our midline, and we return back to our maximum. When we got back to the maximum, that would be the length of the period. We talked about that that's one full cosine curve. Agreed? Max to a max. Okay. So we go from a max, we hit a min, we get back to a max. And this tick mark right here where that minimum's located, how does that compare to the period? Say that again? Halfway. Yeah, that's exactly what it is. It's half of the period. Half here, right? Okay, well, in our data up here, we highlighted a minimum, and we highlighted a maximum. Well, if we were to do that from a max to a min or a min to a max, it doesn't matter the order you go, isn't that just half of a period? So the distance between when this happened, which is in month 1, and when this happened is month 7, is only half of the period, because that's only gone from a minimum up to a maximum. And we would have to return to a minimum to complete that period. So the biggest thing I want you to get out of this is that the distance from the min to the max, or max to min, it doesn't matter the direction you go, is half the period. So in our case, the distance, and distance is always positive, right? So don't worry about the direction you subtract them. 1 minus 7 and 7 minus 1, if we consider it always positive, is still 6, right? So our distance from max to min would be 7 minus 1, or a distance of 6. We will always need to double to get the period. So our period would be 12. This is, if somebody's going to forget something, that's probably what you're going to forget. Double to get the period. Once we know the period, finding B does not change. 2 pi divided by the period, which in this case is 2 pi divided by 12, or pi over 6. Now, as much as I would love to say that a year is always 12 months, that half is always going to be 6, double is always going to be 12, real-world data, especially as we really get into real-world data, does not play nice with that. And so you do actually have to find the distance. It's not always going to be a period of 12 as you work with real-world data, and that's okay. B values, again, kind of ugly on this one, pi over 6. It'll be pi over 6 a lot of times, not always. Okay? And these are your x values. Move along our x-axis for marking the period. All right, any questions on that before we move to our next one? There's A and B. Let's talk about C. C is the easiest and then also the most confusing for people. Okay. If I were to graph this data, again, kind of like I had before, we started down here, we worked up to here, and then we kind of worked down to there. right? C talks about where I start either a sine or a cosine curve. Well, if I were to draw in my midline, unless I knew that some data hit that exactly, it's really hard to figure out where a sine curve would start. But isn't it really easy to figure out where a cosine curve would start? It's going to start at the maximum point. Okay, so to make the phase shift super easy on this, you have to write it as a cosine curve so that this can be where the max happens. However you want to write that. Okay, these again are x values. Where, right or left, am I going to start this? Well, if I choose to write it as a cosine curve, the C, our phase shift, is where the max happens. And our max happens on or at month 7. So as long as I write it as a cosine curve, my phase shift is really easy. No thought process. So we don't have like a formula or anything like that. You just have to remember 2 parts to it. Cosine, maximum. Yes?
So it's like the very first month. Okay, let's say we use minimum instead. If we do x minus, or what did you do?
1.
So it doesn't have to be 0.
No. It'll always be minus because we're going to move to the right when we write it into the equation. And so, with that being said, every single equation you write from data will be cosine. And a day from now or 10 minutes from now, somebody's going to ask me, why is it cosine? Or is it always cosine? And the answer is yes, always cosine. So if I hand you data, your equation is going to be which one? Cosine, always, so that your phase shift is easy, where the max happens, okay? Last letter, D. D goes back to vertical, right? Because this is going to be our vertical shift. How far up or down is our graph moving? So we go back to looking at our Y values. Again, we'll highlight for ourselves. You'll just keep this in mind the entire time where your min and max are happening, because that's what is driving the entire thing here. Now, there is a complex, not complex, but a little bit more cumbersome formula for finding the midline, and that is exactly what it is. It is the average of your max and min. So you could take your max value, which would be 84, plus your min value, which would be 32, and divide by 2. But the other thing is this. If we know our amplitude already, which we do, right? That was the very first number we found. And I know where my minimum value is. Isn't the difference between where my minimum is and where my midline is just A? Okay? So what I could do is go to my minimum value and add the amplitude. I think this right here is the easiest way to find the midline. It's wherever your minimum is plus the amplitude. You could go the other way around. I could come to my maximum and subtract. I just don't like subtracting. So if you do like subtracting, you can do that. But we already found that our amplitude is 26, and our minimum's down at 32. So a second option to find D would be to take your minimum value plus your amplitude. 32 plus 26. I think that's a lot easier to do. You get the same thing regardless of how you go about this, which would be what, 58? Okay, putting it all together. This is just gathering this from the last couple pages we just were writing on. 26, pi over 6. Phase shift is 7. D is 58. All right, sine or cosine? Cosine, not a thought process. And that should be the last time we ask that question, right? Always, always cosine. You will always also need a double parentheses because we'll have a B and a C value. So pi over 6, parentheses, C minus, because we're going to move right, 7, up 58. Now, I do want to give you a little preview because you are going to be asked to use this, and I don't have a question in the notes like this, but looking ahead, once you write this, it's going to say, okay, now this is like a best fit line for the data. You understand that, right? We can't like match that perfectly, but it's like the best fit line for that data. And it's going to say use your model, fancy math word for the equation we just wrote, right? Use your model to predict the temperature in Chicago, which which is where we were doing this for. Chicago in November. Guys, they're not asking you in that question to look at the table and tell me that 49. They can read that. What they're asking you to do is plug that into your function and see what your function says the temperature would be, basically to see how close it is. It should be something close to 49. But let's see how we would do that. I would type in 26 cosine pi over 6. Ooh, what's x if I want the temperature in November? 11. Close that. And then the other thing, so I type that in. It should be something close to 49. But the thing you have to be aware of is anytime we do this, you have to be in radian mode. Okay, so if you are not in radian mode, it's going to give you a super ugly, weird answer and or not an answer. Yes? To make our phase shift easy. Because cosines are pictures that start at a maximum, then I can just match this number, our phase shift, to where the maximum happened. Is that what I said? Are you in radian mode? Double parentheses? We'll check it. Shouldn't be that far off. All right, the last thing I'm going to do is your first problem on your assignment for you. So find whatever piece of paper you are doing your homework on. We are going to do number 30, well, almost all of 30 together.
You want it in radian?
Yeah.
Right? Okay, good.
Oh, you got rid of it.
That's easy. I can't sit there and go back up to the same applied and type it in every time. Just like that.
We were close. 45. It came out to 45. 49 was what was in the table. That's not. Did you have double parentheses? I don't know what you did. I didn't see. All right, let's talk about this problem. First of all, whoever wrote this problem clearly has never ridden a Ferris wheel, because it's talking about riding a Ferris wheel and taking into data, and they're comparing it to the midline of the Ferris wheel and how high they are. But they said, okay, when you guys, has anyone been on a Ferris wheel? When you board a Ferris wheel, where do you board the Ferris wheel at? The bottom. But apparently on this one, at time equals 0, they are right here. So they're boarding like in the middle of the Ferris wheel, I guess. Apparently, yes, this is some Ferris wheel we have never ridden on. So that's the part that always throws people off, is because at time equals 0, you're actually right here, even with the middle of the Ferris wheel. This is a side view. This is like an end view. You're starting right here. And they're saying that after 2 seconds, you've moved up 14 feet. So after 2 seconds, you're about like here-ish. Okay? And then after 3.75 seconds, you're up here, which would be right there. So this is 3.57 seconds later. Okay, good. And then it starts talking about going back down on the other side. So after then 5.5 seconds, we're about here on our way back down. So let's read the questions. It says, find the time it takes for the cart to return to y equals 0. Y equals 0 is height above the midline. So if we started at 0, we went up to 19, and we're on our way back down. Okay, so if we started here, we went up to 19 feet, and we're on our way back down. If it took us 3.75 seconds to get here, how long to get back to 0? 3.75 more seconds, which is actually 7.5 seconds. Okay, so again, let's talk about how do we get the next question. Find the period of the Ferris wheel. That would be one complete circle. Well, if it took us 7.5 seconds to get halfway around the Ferris wheel, it'll take us 15 seconds. So the period equals 15 seconds. Yeah, making sense now? Sketch the graph representing the position of the passenger cart over one period. So we will sketch just like we are used to. 1, 2, 3, 4. What am I labeling that fourth tick mark as? 15, right? Period. Now, again, what's going to bother you is the fact that they are considering 0 the midline. So that is the midline of this, and you go negative height, I guess, on this Ferris wheel. So as we start this, we start at 0. We go over 1, up 19, right? That was the highest we were hitting here. And then back to 0 at 7.5 seconds, down to negative 19, back to 0. This would be 1 trip around the Ferris wheel. Drawn there? Yeah? So then write I told you we were going to run into that word, right? Sinusoidal. Now sinusoidal means sine or cosine. This one would be
I thought you said always use cosine.
data, if they're given data. This picture I would go with sine, okay? And I would go with sine on this one. You can have a phase shift of what? 0, right? Because at time equals 0, we're at the midline. And our midline, what's our vertical shift? 0. Okay, amplitude? 19. So all you have to do is figure out B and write the equation. The rest of your assignment. I don't know where we're going yet. I haven't even given you your assignment yet. You are on page 264. 9 through 13 is like the first part of our notes. 20 and 22 is the data. 30 you almost have done. You just need to finish out writing the equation on number 30 and it'll be done.